Hi, my name is Chloe Hampson, and today I will be answering a question from the McGraw-Hill-Ryerson Calculus and Vectors textbook. The question is located in Unit 5 and pertains to exponential functions. The particular question is located on page 297 and is number 14. It is about bacteria growth. I will begin by reading through the question once, and then I'll reread the question while highlighting the key elements of the problem. A student grew bacteria in a petri dish as a science project. He estimated the initial population, N0, as 1,000 bacteria. After one day, the population, N, was estimated to be 1,500 bacteria. A. Assume that the growth follows an exponential relation of the form n of t equals N0 times e to the power of k times t. Determine the values of M0 and k, assuming that time t is measured in days. B. How long does it take for the population to double to 2,000 bacteria? C. Differentiate the population function with respect to t. D. How fast is the population growing at t equals 5 days? I will now reread the question to highlight the important information. A student grew bacteria in a petri dish as a science project. He estimated the initial population, N0, as 1,000 bacteria. This is very important as the initial population of the bacteria is 1,000. After one day, the population, N, was estimated to be 1,500 bacteria. This means that N of t after one day is 1,500, where t is 1. Letter A asks us to assume that the growth follows an exponential relation of the form of n of t equals N0 times e to the power of k times t. It says then to determine the values of N0 and k, assuming that time t is measured in days. This question is very important for us to answer questions B, C, and D. Looking at the equation, we know that n of t is equal to the bacteria population after t days. We know that N0 is 1,000, which is the initial amount of bacteria. We know that k is the growth constant, and then that t is time in days, as stated in the question. B asks us how long it takes for the population to double to 2,000 bacteria. This is asking us to find t when n of t is equal to 2,000. C asks us to differentiate the population function with respect to t. This means that we will need to find the derivative of the original equation given. Finally, D asks us how fast is the population growing at t equals 5 days. This is asking us to find the rate of change of the bacteria population at t equals 5 days. In order to solve this problem, I will be going through each part individually, beginning with letter A and then ending with D. In A, I will be solving for the unknowns. In this case, k as N0, t and n of t are all given to us in the question. To do this, I will substitute all the known values into the equation and then proceed to solve for k. In B, I will be finding the time at which the population of bacteria doubles to reach 2,000. In order to do this, again, I will substitute the values I know into the equation and then solve for time. In C, I will be differentiating the equation. In order to do this, I will need to use the chain rule. In D, I will be finding the rate of change at the time of 5 days. I will need to substitute the known value of t into the derivative equation and then solve for the rate of change. To begin, I will solve for letter A. To reiterate, here I am asked to determine the values of N0 and k, where t is time in days. Again, we know that n of t is the bacteria population after t days. We know that t is time in days. We know that N0 is the initial amount of bacteria. And we know that k is the growth constant. From this question, we are given that N0 is 1,000. This is the initial amount of bacteria, as stated before. We are also given the amount of bacteria after one day. This number is 1,500, and therefore we know that n of t is 1,500, where t is 1 day. With this information, I can substitute these values into the equation in order to solve for k. Now, to solve for k, I will first divide both sides by 1,000 in order to begin to isolate for k. The next step is to take the natural logarithm of both sides in order to further isolate for k. After this, we are left with k equals ln 3 over 2. Therefore, we have determined that N0 is equal to 1,000. This is the initial amount of bacteria in the petri dish, and k is equal to ln 3 over 2, and this is the growth constant. Now I will move on to letter B. in which I am asked how long it takes for the population to double to 2,000 bacteria. N of t is a bacteria population after t days. Therefore, N of t equals 2,000, where t is what we are going to solve for. From letter A, we now know that k is equal to ln 3 over 2, and n naught is equal to 1,000. With this information, we can substitute these values into the equation and solve for time with respect to n of t. To do this, I will follow the same procedure as last time and substitute the values that we know into the equation. Like last time, I will divide both sides by 1,000 and then take the natural logarithm of both sides. Then I will divide both sides by ln 3 over 2 in order to finally isolate for t completely. I am left with t equals about 1.7. Therefore, it takes approximately 1.7 days for the bacteria to double to 2,000 bacteria. Letter C now asks me to differentiate the population function with respect to t. This means that I will need to find the derivative of the equation. To find the derivative of this equation, I will have to find the derivative of the exponent as I must apply chain rule, which is the derivative of the outside multiplied by the derivative of the inside. I must find the derivative of ln 3 over 2, which is derivative of the inside, and bring that down, and then find the derivative of e to the power of ln 3 over 2t, which is the derivative of the outside. We know that e to the power of ln 3 over 2t is the same as the derivative of e to the power of x, and therefore it is unchanged. However, because we must apply the chain rule to the equation, I must bring down the derivative of ln 3 over 2t. This is just ln 3 over 2. With that, I have differentiated the population function. I keep the constant 1,000 at the beginning of the question as it is multiplied by the variable and therefore does not change. This 1,000 is followed by the derivative of the outside, which is e to the power of 3 over 2t, and then multiplied by the derivative of the inside, which is ln 3 over 2, as the chain rule states you must do. Finally, letter D asks how fast the population is growing at t equals 5 days. This means that the rate of change is at 5 days. In order to solve this, we must use the differentiated function that we found in letter C. To find this answer, we will substitute 5 in for t into the derivative equation. I will solve this using my calculator. To find the answer, it's about 3,079. This means that, therefore, the population of the bacteria is growing at a rate of 3,079 bacteria per day. This completed question is the type of problem that might be solved in daily life in a science lab. A biologist, for example, might need to calculate the population growth of his or her bacteria and may need to use an exponential equation to do so.